Well, we've got good news and bad news. The good news is Harold is out of the hospital. The bad news is Maude is in jail. It turns out it's considered assault if you bonk somebody on the head with a ladder. Okay, so Maude is going to try to break out of jail. This is the window of her cell. She's going to rappel down. It looks like she's a little unclear on the concept because it looks like she's attached the rope to the top of her head, but we'll go with it. Okay, she's going to rappel down. Now Harold is standing over here. He's 100 feet away, and he's shining a spotlight, that's this right here, a spotlight on her. Now, it's not 100% clear to me whether he's trying to help or hinder her here. He might be shining the light to help her escape because they are such good friends. He might be holding a little bit of bitterness about the fact that she conked him on the head with a ladder, so he might be shining the spotlight to say, hey guards, see her, catch her, put her back in jail. I'm not sure. We'll have to ask them if we ever get a chance. Okay, but that's what's happening. Okay, and then we're told that Maude is rappelling at a rate of 2 feet per second. So she's going to be coming down at 2 feet per second. I want to know how fast the angle of elevation for the spotlight, that's this thing that I've marked as theta here, is changing when she's 10 feet off the ground. Not immediately clear why I care about this at the moment that she's 10 feet off the ground, but there are many things about Harold and Maude that are not immediately obvious to me. So we'll go with it. Okay, now this is the first time we're doing a related rates where there's an angle involved. So I need to remind you that when we are doing calculus, we are in radians. Now, if I'm just doing algebra or trig, it doesn't matter. Sine of 30 degrees and sine of pi over 6 are exactly the same thing. It's 1/2. But the limit as x goes to 0 of sine x over x equals 1 if x is in radians. When we derived this using squeeze theorem, we used that the angle that corresponded to a full revolution was 2 pi. We did not use 360. We worked in radians. Okay? So this result is valid in radians. If we were measuring things in degrees, we would still get a finite limit, but it would be a different number. We just have to convert this to degrees. Okay? But this limit got used in figuring out the derivatives of sine and cosine, which we then use to get the derivatives of the other 4 trig functions. So anytime we're doing calculus with trig functions, we must be in radians. Okay? Now, that's perfectly fine, but very often we're going to be given problems or asked to give answers in degrees instead. In fact, here I'm going to adjust the directions here and say give the answer in degrees per second. Okay, that's fine. I just have to recognize that when I solve the problem, theta is in radians, theta prime will be in radians per second. If this is the version that I want, I will have to convert. That's all. But very important to recognize that if you are using any of the calculus formulas for trig, you must work in radians. So often you're given a problem in degrees, convert to radians, do the calculus, convert back to degrees. Okay. So here I want to take a look at what's changing. Now obviously I need to know how fast theta is changing, and it looks like what I know is how fast Maude's height is changing. So I'm seeing that at every moment in time, I'm going to have a triangle that looks something like this. Here's theta. This side right here is always 100. Harold's not moving forward and back with his spotlight, but Maude's height, I'll just call that M, Maude's height off of the ground is changing. So what I have here is a right triangle. Now we've had right triangles before, and we've used Pythagoras. So sometimes people immediately jump to Pythagoras. But the Pythagorean theorem doesn't contain an angle, and I need to know how fast the angle is changing. So sometimes when you have a right triangle, you are using Pythagoras. That's when you care about just the side lengths. But if you're concerned about the angle, you're probably going to be using a trig function. I've got this angle, I've got the opposite side, and I've got the adjacent side. So that makes me think tangent. So I'm going to say tangent of theta is m over 100. And I think I'm just going to multiply both sides by 100. So we'll get 100 tangent of theta is equal to m. Excellent. So I'm going to take the derivative with respect to time of both sides. Theta and m are my two functions of time. Okay. So the derivative with respect to time of 100 tangent of theta is equal to the derivative with respect to time of m. Now if I'd kept the 100 here, that would be fine as well. I probably wouldn't, though, use quotient rule here. I would say that's the same as 1/100th times m, and then I could use constant multiple rule. So you want to be on the lookout for shortcuts like that. All right, so here we get constant multiple rule. We keep that 100. Derivative of tangent is secant squared, so we'll get secant squared theta. Chain rule times a theta prime. And then the derivative of m will simply be m prime. Okay. All right, let's see. So I'm going to just clear some space. All right, 100 secant squared theta times theta prime equals m prime. I want to know theta prime, so I need to plug in for the other things. Okay. Now, one thing to point out here, I don't care what theta is, I care what secant of theta is. So we care at the moment in time where this is 100 and Maude's height is 10. Okay. Now, I could describe theta there. I could say that's going to be arctan of 10 hundredths or arctan of 1/10, but it's not necessary for me to do that because I just need to know what secant of theta is. Secant would be hypotenuse over adjacent, so I want to know the hypotenuse. Okay. Well, 10 squared plus 100 squared equals the hypotenuse squared. That's 100. That's with 4 zeros, 10,000 equals h squared. So 10,100 equals h squared. The hypotenuse is positive, so it's the positive square root of 10,100. Okay, so then I can say that means secant of theta is square root of 10,100 over 100. Okay, so plugging in, which I'll do over here, I've got 100. We're going to take secant and then we're going to square it. So it's the square root of 10,100 over 100, quantity squared, times theta prime equals m prime. Now we were told Maude's repelling down at a rate of 2 feet per second, so I know the absolute value of m prime is 2. Let's see, is Maude's height from the ground increasing or decreasing? It's decreasing, so m prime is negative 2. All right, so this is 100 times. When I square this, I'm going to get 10,100 over 10,000. Theta prime equals negative 2. I can cancel. The 100 will cancel here and get rid of 2 zeros. Can cancel another 100 here. So we get 101 theta prime equals negative 2. Theta prime equals negative 2 over 101. Okay. All right, that's my math answer in units of radians per second. Because remember, it's going to be the units for theta divided by the units for time. But theta, since we used some calculus to say the derivative of tangent was secant squared, theta had to be in radians. So I want to change the units before I state the answer in words. So I'm going to just multiply by 1 in a form that doesn't look like 1, but it's going to be the same thing over itself. I want to get rid of radians. So I'm going to say pi radians. That would correspond to half of a revolution. But I know that happens to be 180 degrees. Now usually I don't write in the units of radians. I'm doing that here because I'm really focusing on the units. That's going to cancel the radians. Okay. So we will end up with negative 360 over 101 pi degrees per second. That's theta prime in the right units. Notice it's negative. That makes sense because in order to follow a person who's coming down, the angle would be decreasing. So we can just say the angle is decreasing at a rate of 360 over 101 pi degrees per second. So we use the absolute value because the word decreasing accounts for the negative sign.